Hello everyone. So far we studied the different measures of central tendency like the mean, the median and the mode. There's another measure which is very important in the study of statistics that's called the variance, and with it is related the standard deviation. What this refers to really is the variation among the individual data values from the average of the data values, right? So it's the variation among the data values or within the different individual data values in the data set. And we will learn how to calculate the variance and standard deviation using two different methods. One will be the defining method, the other one is the computing method. So in this lecture, we will talk about the different measures of variation. There are three kinds. One is a very simplistic measure, which is called the range, and that's nothing but the difference between the lowest value and the highest value in the data set, which is calculated by just taking the highest value, the maximum value, and from it we subtract the lowest value, which is the minimum value. So it tells us the variation between just two values in the data set, the highest value and the lowest value. It does not really tell us much about how the other values in the data set vary from each other, right? For that, we have to learn about variance. What is the variance? The variance finds the the average squared value. So it refers to the average squared deviation, and that word squared is important here. Average squared deviation of the individual values from the mean of the data set, of individual values from mean of the data set. And with the variance, along with variance, we have what's called the standard deviation. What is standard deviation? Standard deviation is the average deviation of individual values from the mean. All right, so there's no squared in the standard deviation. So let me write that here. It's just the average deviation of individual values from the mean, of values from the mean. So the standard deviation is an unsquared form of the variance, right? So we will talk about that at length as we go through this lecture. And at the end, we will also discuss the different distribution types that the data might have, as well as the shapes of the associated curves, which are derived from the histograms when we organize our data. So let's start with the range of a data set. The range of a data set is the difference between the lowest and the highest values of a data set. The range is given by the formula range equals max, the maximum value, or the highest value in the data set minus the lowest value. Right, so it denotes the maximum and minimum observations respectively. So it tells us about the variation just among two values in the data set. It does not tell us how much the other values vary from each other, right? Let's look at this example here on two teams of basketball players and their heights. This will give us an understanding of the range and some of its drawbacks. All right, so we have here two teams of 5 members, 5 players in each team, and they have their heights listed here in inches, in both feet and inches, but we look at the one with inches in it. All right. So if you calculate the mean height of these 5 basketball players in team 1, we get a mean of 75 inches. In team 2, if you find the mean, add up all the values and divide by 5, you will get a value of 75 inches. So both the teams have mean height of players at 75 inches. However, if you look at the range, the variation among the height of the tallest player and the shortest player in team 1, then it's 78 minus 72, correct? So let's write that down here. The range, which is the difference between the maximum and the minimum. So 78 minus 72, 78 minus 72 equals 6, correct? For team 2, if you look at the range, then that's 84 minus 67, correct? So that would be 17 inches. So the difference in heights between the tallest player in team 2 and the shortest player in team 2 is 17, whereas in team 1 it is 6. Right? So even though the means are the same, the average heights are the same, you would think that, well, everybody has the same height pretty much there. The heights between the two teams are the same. But when we calculate the range, we see that team 2 has a higher range, a higher difference between the tallest person and the shortest person than team 1. However, look at the heights of each member in team 1 and each member in team 2. We see that in team 1 we have the heights, the players are more or less the same height. The heights of individual players are closer to each other than that in team 2, right? Here we have taken out the tallest person and the shortest person from each team to calculate the range in the data set. So 78 was the tallest person in team 1. 72 was the height of the shortest person in team 1. And we have the range value as 6 inches in team 2. The difference between the tallest and the shortest is 17 inches. However, the drawback of the range is it's only comparing the heights of, or comparing the values of two members in a data set. We are not even bringing in factoring in the heights of the other players that were in team 1 or in team 2. Right? So that's the deficiency of using the range to understand the variation. It gives us the variation between just two members in our data set. It does not tell us about the other members in the data set. Now we saw that the range gives us the variation among two data points in our data set, the highest value and the lowest value. It does not tell us anything about the other values in the data set. For that, we have to look into or study variance and standard deviation. So let's try to understand the definition of the standard deviation. It says here the measure of standard deviation is the average deviation of the individual data points or observations from the mean. So what it does is we have to first know the mean of our data set. which will be, and we are talking about sample standard deviation. The formula given here is for that of the standard deviation. Rather, the sample standard deviation is what I meant to say. But we can also find the standard deviation of the population, and that's slightly different formula. But let's talk about the sample standard deviation, because most of the time we'll be working with the sample. All right, so what this does, this formula does, is it first calculates the mean of the data set denoted by the symbol X bar. And then it takes each individual data point, and finds how much it is off from the mean of the data set. All right, so it calculates the deviation of each individual value from the mean, or rather, how much they are off from the mean. Remember here, it says it's the deviation of the individual data points or observations from the mean. So we have just done this part here. All right, deviation of the individual. So that's what x sub I minus x bar does. It calculates individual deviations of values from the mean. But then it says it's the average. All right, so what do we do when we calculate the average? Remember, average is the summing up all the deviations. It would mean sum of all the deviations divided by the number of deviations we had. All right, so sigma x divided by n. All right, so that's why you see over here we have a sigma, that is summation, and we also need to square it. Now, when we work through an example problem on standard deviation, I will tell you exactly why we need to square the deviations. We will first need to square our deviations, and only then we will need to find the sum, the total, and then we divide it. Instead of n, we divide it by n minus 1 when we are trying to find the sample standard deviation. And you will see that happening very often in statistics, in fact almost always. Whenever we find the sample standard deviation, the denominator will, instead of using just n, it'll be n minus 1 or n minus 2, and so on, as the case may be. All right, so the reason for not using n but using n minus 1 is that it gives us a better estimate of the population standard deviation. Right, that's the reason for it. It's a little bit complex concept, but for this course we just know that we subtract 1 from n for sample standard deviation, because it is an unbiased estimator. In other words, it gives an estimated value which would be closer to the estimated population standard deviation. All right, so note this is the formula, and we have to take the square root of this expression here, because we had ended up squaring our deviation. We have to undo it and take the square root of it. So that's the sample standard deviation. It is the average deviation of the individual data points or observations from the mean. Now we have learned about another term here, which is the variance. The variance is the squared average deviation. So in other words, variance is, all right, here I have it here. Variance is the squared standard deviation. So it's S squared. For sample standard deviation, we just use S. For variance, it's S squared. It's everything before taking the radical, or before taking the square root of this expression. That's what variance is. All right, so we will be working step by step through the process of finding the standard deviation, and variance is the value we get just before the last step when we go and take the square root. All right, so we'll go through an example like I said. Now the formula that we saw previously was the defining formula of the standard deviation because it follows closely the definition of the standard deviation. There's another formula also called the computing formula, which is a variant of the defining formula. It's derived uh, from the defining formula, but it does the same thing pretty much, but this is a faster way and more efficient way of calculating the standard deviation, and this is sigma x squared minus sigma x whole squared divided by n over n minus 1, and then it's the square root over the entire expression. Again, we will work out examples in a worksheet separately using both the defining formulas and the computing formula. We'll now talk about the distribution of data. We've seen this particular slide before when we were talking about the measures of central tendency, but let's go over it and review it because we need to understand the distribution of data. That's very important. So a symmetric distribution is one when the mean and the median are equal values or almost equal, very close to each other. In that case, what's going to happen is 50% of the data values are going to be concentrated on the left-hand side of the center point, and 50% are going to be to the right of the center point. Again, the mean and the median would be located right at the center. They are the same value, they will be located at the center, and it has an equal distribution of values on either side of the center point. That's a symmetric distribution, and when we draw a curve over the histogram, as we see here, we don't see the rectangular bars, but a distribution is nothing but a curve drawn over a histogram, and then we just remove the bars, so to speak. All right. Now, in a right skewed distribution, that happens when there is a high concentration of data values on the left hand side. So we see the curve peaks on the left and it has a long tail to the right. And that happens when the median is less than the mean. The median is a value which is less than the mean. In that case, we call it a right skewed distribution. And just to remember, the right skewed distribution will have a long tail to the right, and the concentration of data, the peak will be on the left hand side towards the left. In a left skewed data, the median is a value higher than the mean. Median is greater than the mean, and we see here the concentration of data is more on the right hand side than on the left hand side. It has a long tail to the left, therefore we call it a left skewed distribution. So let me give you an example of right skewed and left skewed distribution when that can happen. So if I give you a test and the students find the test very difficult and the scores in the test are low, right? Most of the students have scored, let's say, in the 60s, 50, 60, and 70, and just a few of the students, one or two of the students, scored higher than the mean. All right, that means, let's say, just a couple of students score in the 90s and the rest are all low scores, 60, 70, and so on. That would cause a right skewed distribution of the scores. That means the test was perhaps pretty hard, difficult test for the students, so most of them scored low, and therefore it becomes a right skew distribution. If I give a very easy exam to the students and they end up scoring very high, most of the students are scoring in the 90s on the test, then what has happened is it's a case of left skewed distribution. That means most of the students have scored pretty high, and there are just a few students who scored low. All right, so that's kind of an example of what can cause a right skewed or a left skewed distribution. And a symmetric example of a symmetric distribution would be if the test was just right and there were equal number of students that scored below the mean and those that scored above the mean, right? An equal distribution, so to speak. Now, before continuing with the distribution of data, let's look at the relationship between the standard deviation and the, the standard deviation value and the spread of data. All right, so here we have two sets of data, data set 1 and data set 2, and we do the calculations for data set 1. So x bar, the sample mean, for data set 1 is 50. Well, for data set 2 it's 50 also. But look at the standard deviation values. For data set 1, the standard deviation value is 7.4. For data set 2, it's 14.2. So what does this tell us? It tells us that higher the value of the standard deviation, greater is the spread of the data values, the spread from the mean of the data values. So when we show it graphically using a curve, the standard deviation, which is a lower value, will have a tall curve, right? It will have a tall curve, tall and narrow curve, so to speak, with the mean at the center, and most of the other values are closer to the center, to the mean, right? On the other hand, if it is a value which is larger standard deviation, then this is how the distribution or the curve is going to look like. It's going to be a broader spread of values with a smaller peak. All right, so this would happen. All right, this case would happen for a standard deviation value which is large, and a narrow and higher peak would happen when the standard deviation value is small. All right, as you can see over here in the second diagram, we have the mean at the center, but the data set is spread out far from the mean. Okay, so again, keep that in mind. Higher the standard deviation, greater is the spread of the values from the mean. Lower the standard deviation value, we have the distribution of individual values closer around the mean, around the center point. Here we are showing the spread of the data points from the mean using a dot plot. You should be able to recognize this. It's a dot plot that they have shown. They've shown the mean at the center, and they're showing the values over here. They're showing the values. Now data set 1 had a standard deviation of 7.4 and data set 2 had a standard deviation of 14.2. All right, and they have scaled the horizontal line showing the mean at the center and then adding the standard deviation values. All right, so this distance here on the right hand side, this distance from the mean, which is one standard deviation away, all right, this is one standard deviation away, is whatever the mean is plus the standard deviation, right? So the mean was 50, or the mean is 50. They've added one standard deviation, 7.4, and come up with 57.4. All right. On the left hand side, it's the mean minus the standard deviation, because the values to the left of the center point will be less than 50, right? So it's x bar, so 50 minus 7.4. 50 minus 7.4 for a value of 42.6. So this is how they have scaled the horizontal line. So then the next interval is at x bar plus 2 times s. So that means 2 times 7.4, that's 64.8. And then finally we have x bar plus 3 times s. So we have scaled the horizontal line 3 standard deviations away from the mean and on the right hand side, and 3 standard deviations away from the mean on the left hand side as well. All right, for data set 2, they've done the same thing, but they have used a standard deviation value of 14.2, which was the standard deviation value for data set 2, right? But look at the spread here. All right, we see that these dots are spread out further from the mean than in data set 1, right? We'll now talk about a special rule called the 3 standard deviation rule. And this tells us about the distribution of data, the proportion, the percentage of distribution of data along the curve. All right, so let's go through this. The 3 standard deviations rule tell us that almost all the observations in any data set lie within 3 standard deviations to either side of the mean. In other words, what it's telling us that the 100% of the observations that we have will be covered by this curve within -3 standard deviation on the left hand side and +3 standard deviation on the right hand side. And that is the reason when we draw our distribution curves, we do not go beyond -3 and +3 on each side. All right, -3 standard deviation and +3 standard deviation, that is, right? Because almost 100% of the observations will fall under this curve. Very rarely there will be one observations, and that's very, very low probability when an observation will lie beyond the ±3 standard deviations, but almost 100% will be covered by within the 3 standard deviations. And then this goes on further to say that 68% of the observations will be within ±1 standard deviation. See, most of the about 68% will be within ±1 standard deviation. 95% will be within 2 standard deviation, ±2 standard deviations, and 99.7% will be within ±3 standard deviation. Now you have to remember these percentages because we need to apply them to solve some statistical problems on assignments and tests. All right, so just memorize these values. So plus minus these percentage values, that is plus minus 1 standard deviation will see 68%, will cover 68% of the data set of the observations. Plus minus 2 standard deviations will encompass 95% of the observations, and plus minus 3 standard deviations will be 99.7%, which is almost, like I said before, almost 100% of the data observations will be within that range, within x bar minus 3s and x bar plus 3s. All right, s being the standard deviation. The three standard deviation rule is also called the empirical rule. And here we just state what we discussed just now on the three standard deviation rule. So let's read through it. For any quantitative data set, again, it has to be quantitative data set with roughly a bell-shaped distribution. Bell-shaped distribution is a symmetric distribution. The following properties hold. Number one, approximately 68% of the observations lie within one standard deviation to either side of the mean, that is between x bar minus s and x bar plus s. Property 2 says approximately 95% of the observations lie within two standard deviations to either side of the mean, which is between x bar minus 2s plus x bar plus 2s. And then number 3 says approximately 99.7% of the observations lie within three standard deviations to either side of the mean, which is between x bar minus 3s and x bar plus 3s. Let's talk a little more about the distribution of observations and the different shapes it can take. Normally, the distribution is graphically represented as a curve over a horizontal line. If it is a normal distribution or a symmetric distribution, then it'll be a bell-shaped curve, which is very symmetric. That means if you draw a line through the middle of the curve, then it'll be a kind of mirror image. Both sides will be the mirror image of each other. All right, so that's what symmetric curve is. This is a picture of a symmetric curve, and we have here on the horizontal axis the values of the different observations in our study. This study is about the height of people or players in inches. So these values that we have on the horizontal line are heights, different values of the heights, observed heights in our study, from our study. And the vertical axis has the relative frequencies. Now we have done distributions, we have represented distributions before in the form of histograms, right? We already learned about it in the previous chapter where we spoke about how to represent the frequency of observations graphically in the form of histograms. So what you see inside the curve here, these vertical bars are nothing but a histogram. So the way we go about it is we create a frequency table, find out the frequency of observations for the different values, and then from it we create a histogram, and then we superimpose a curve over the histogram. And generally what we statisticians do is they remove the vertical bars, the histogram, and just keep they just keep the curve. So that's why we see a picture of a curve. Now, distributions are not always symmetric. They can be skewed. They can be right skewed or left skewed. and they can come in different shapes. Does not all may not always be a smooth curve like you see in this picture. All right, so let's quickly read what this says here. The distribution of a data set is a table. It can be in the form of a table, like a frequency table, a graph, which is this picture here. A histogram is kind of a graph, and this curve is also a graph. Uh, or a formula. It can also provide a formula that provides the values of the observations and how often, how frequently they occur. Now, distribution shapes can be classified based on the number of peaks that a graph might have. We are given three pictures here. The first one is an example of what's called the unimodal distribution. In a unimodal distribution, the graph will have a single peak, only one peak. As we see here in the picture, the graph rises up to a certain point and then drops and doesn't rise again. All right, so it has a single peak, it's unimodal. In the second picture here, it's called the bimodal, bi meaning two. It has two peaks. To give you an example of this kind of distribution, think about when the enrollment period opens in the middle of the semester for the upcoming semester. As soon as the enrollment period starts, we see a sudden rush of activity of students going into the systems and registering for the different courses, so they get the best timings and the professors they want to take the courses with, and so on. So there's a flurry of activity immediately after the enrollment period opens. And then once the early bird registration is done, there is a drop in the activity to enroll. So we see a drop, and then students get busy with the exams and so on. And then maybe a few weeks before the enrollment, before the semester begins, the next semester begins, we see a flurry of activity come up again. So there is a peak, there is a rush of students trying to enroll into the classes. So we see the graph going up and peaking, and then after the semester starts, there's a drop in the enrollment activity, in the enrollment process. So that's an example of bimodal distribution. The third one here is an example of multimodal, where we have more than two peaks, several peaks. And that example, to give you an example of that, would be the uh, uh, the sale of the sales in a store. All right. So there are periods when stores offer sales, like the Memorial Day sale. We can see a peak of activity. And then after the sale is over, Memorial Day weekend is gone, we see a drop in the sales. And then again, before the Labor Day or maybe the July 4th weekend, we see again the sales going up. And then it comes down. And then the Labor Day sales come, then it goes down after that's gone, and then maybe Christmas again we see a peak, and so on. All right, so that's an example of multimodal distributions. So if you are asked, given graphs like this, and asked to identify what type of distribution it is, please look at the number of peaks in the graph and decide accordingly. All right, if it has two peaks, it's bimodal. If it has more than two peaks, then it's multimodal, and one peak is unimodal. Now, symmetric distributions can come in different shapes. We already know about the bell-shaped distribution, bell-shaped curve, which is symmetric, and it takes the shape of a bell. It's a smooth curve, all right? So that means there are values at every point on the curve. The other kind of shape of symmetrical distribution would be a triangular shape, all right, where we have some values at the extreme ends, and then most of the values are focused around the center. And the uniform or rectangular distribution is one where you have every observation occurring an equal number of times. It's a uniform distribution. We've already talked about the asymmetrical distributions before, but let's go over it one more time before we finish this section. A right skewed curve is one which has a peak on the left and a long tail to the right. A left skewed curve has a long tail to the left and it peaks on the right. So that's how you can remember or the left skewed and the right skewed curves. A right skewed curve will have a long tail to the right and a left skewed curve would have a long tail to the left. And these are, as you can see, not symmetrical distributions. These are asymmetrical distributions.